Welcome to your first lesson regarding chapter 19, which is chemical thermodynamics. We did the energy part of thermodynamics way back in chapter 5, and we are going to learn more about energy in this unit. The first thing we need to define here is entropy. And I think I gave you a short version when we were talking about solutions and why things dissolve. Okay? There's a technical definition of entropy right here. Generally, we call it randomness or disorder. Okay? And actually, what it really is entropy is higher when a substance is, let me pause this and write. So when a substance has many different arrangements and energies of particles, its entropy is said to be higher. Okay? So in general terms, solids have less entropy than liquids, which have less energy than gases, if you're talking about the same substance, a specific pure substance, because the solid arrangement really only has a vibrational energy, and they're very tightly packed and they're not moving anywhere, so they can't really arrange differently. Liquids have more options for arranging and add the rotational on top of the vibrational motion. And gases have rotational, vibrational, and translational motion. And because they're freely separated from one another, the particles can arrange and twist and turn in many, many different directions. In terms of the relationship of entropy to temperature, the lower the temperature, the less entropy a system has, because the particles have less energy of whatever kind. So these arrangements and energies we will call microstates, okay? And the more microstates are possible, because there are more energy possibilities, more vibrational and rotational possibilities, and because the particles are farther apart from one another, okay, the number of microstates will increase for the following three reasons: increasing volume, increasing temperature, or increasing the number of particles, because that allows for more arrangements and more energies. So that's kind of maybe a simple way to look at it, I hope. Maybe not super simple, but I hope it'll become simple eventually. This is a nice diagram right out of your book showing the increase in entropy based upon the structure of water in the solid, liquid, and gas states. Okay? So definitely please take a look and read these. Pause the video and read these over. Make sure that you're clear on what is being depicted here, okay? Because it's kind of important. So let's look at 4 processes and see whether we can predict whether the entropy is increasing or decreasing in these, okay? And the symbol, by the way, entropy has the symbol S0. That means it's standard conditions. And an entropy change would be called delta S. So we're trying to determine, is entropy increasing or decreasing? Is delta S positive or negative for these processes? Take a look at the first one. You notice that a liquid is turning into a gas. Well, 2 things are happening. The molecules are gaining another type of motion and they're becoming more spread out. So in this case, entropy is increasing. Check out the second situation. This represents a precipitation reaction where I have ions that are moving freely through a solution that are suddenly transferred into a rigid solid with a highly ordered crystal. That represents a decrease in entropy. Okay? Here, you notice that I have some gas at the beginning that I don't have at the end. And so I'm going from a system for which part of the substance is in the gas state to no gases. Therefore, entropy is decreasing here. And this one is a little tougher to determine. We have 2 molecules here. We have 2 molecules here. They're all in the gas state. And I'm going to say that we really can't tell if we don't have some data for this one. So it's really not possible to have a clear qualitative prediction. So now we should talk about calculating an entropy change. And in order to do this, you need to go to page 1088 or Appendix C in your book. Okay, so pause the video and get that page open, please. Now you already know how to use the column of values labeled as delta H of formation, because we learned how to do Hess's law back in chapter 5, and that's the usefulness of, in this table in the appendix, the first column of values labeled as delta H. Okay, that's the use of those. We're going to skip that middle column for a minute, and I want you to look at the third column, which is standard entropies. Okay? These are entropies, absolute entropies for substances at 25 degrees Celsius. Okay? So, a couple of things. First of all, the units are different. Joules per mole Kelvin, because these values are temperature dependent. As we said earlier, changing temperature changes an entropy value. Okay? And these are also measured in joules rather than kilojoules, which means these numbers tend to be somewhat less significant than the delta H and delta G values that you see, because their units are 1/1000th of the units of the other two columns. In this table, please look up the two values, please, for the standard entropies of bromine monatomic and bromine diatomic gases. You will see that the value for the diatomic bromine is greater. Okay, and this is because the two particles bonded together, as opposed to a single atom, allows for a different kind of rotation and spinning and jiggling of the bond farther and closer and all sorts of things, right? So there are more microstates possible in this diatomic bromine with two atoms that can wiggle their arrangement more than a single atom can. At this point, I would say pause the video and read these statements about how entropies change with respect to those examples, and jot down questions in your notebook if you have any, and you can bring those up in class. So there is an equation that allows us to find the delta S, or change in entropy for a process. And this equation looks very much like Hess's law that we used back in chapter 5. Delta H of a reaction can be found by summing up the enthalpies of formation for the products minus the reactants. And actually, I kind of should have done that. Sum of entropies for the products minus sum of entropies for the reactants. Okay, this equation is also on your equation sheet, so you don't have to memorize any of this. So let's take this first example and calculate delta S using the values from Appendix C. Pause the video now, look up the values, calculate an answer, and see what we end up with. So here we have the values that I found on the table, and in this case, notice because there is 1 mole of the reactant and 1 mole of the product, what happens in this solution is that the moles cancels for both of these, and I end up with a unit of joules per Kelvin for my delta S. Notice also there are no negative entropy values. The lowest entropy a substance can have is defined as 0. So I'd like you to do the same thing now for this next example. You will have some coefficients here that are not 1, and so that will affect your math. Look up the values and calculate delta S, please. At this point, just verify that I have pulled the right numbers. I'm pretty sure I have. Okay, set them up. I will do the unit cancellation. The moles will cancel on all of these. Notice that I pulled down my coefficients from the balanced equation. And so at this point, all that is left to do is the math and get an answer in joules per Kelvin. Okay? That's what I'm getting. I'm rounding away my decimal places. Double check that and just make sure. But at that point, it's math. I'm really more interested in the setup than the math right now. This slide here really gives you a statement of the first, second, and third laws of thermodynamics. Okay? The first law of thermodynamics we did in chapter 5, and that was that little concept about how the energy change for a system is the sum of both the heat it either absorbs or releases and the work that it either does or is done upon it. Okay? The second law is that it is the nature of the universe that the entropy of the universe is increasing as spontaneous processes take place. We'll talk about that more as we move on. And the entropy of a pure crystalline substance at absolute zero equals 0. So there are no negative entropy values. You won't need to know these by name, by the way. So let's talk real briefly about what we mean by a spontaneous process. Okay, and that word is not a science word. That's just a normal English word. And I think you can probably understand the definition is that's a process that happens on its own without any outside assistance. Okay? So I drop a glass, it breaks. Salt dissolves in water. Alcohol evaporates. Okay? Things that just happen without help are spontaneous. Took a lot of walks in the woods over the spring break. And there are piles of leaves, and there are logs that are decomposing over time. The snow is melting when the sun shines on it. All of those are spontaneous processes. They just happen. Now keep in mind these two things. It is not true that spontaneous means fast. We studied rates in chapter 14. And it is not true that if it's non-spontaneous, it's impossible. Because a non-spontaneous process can be helped. If we provide the outside assistance, it can in fact take place. Last little bit for this lesson, we will learn that spontaneity is a consequence of two factors. Enthalpy change, like we talked about in chapter 5, and entropy change, like we are talking about now in chapter 19. And so we will put together the enthalpy changes, otherwise known as delta H, and entropy changes, and it is going to be a balance between these two factors that determine whether a reaction is spontaneous or not.